This right here, this topic is nothing more than revisiting thermochemistry. So if you took general chemistry, you guys covered thermochemistry. And the most important part about thermochemistry was understanding how we look at the universe. And hopefully it will jar your memory that when we're looking at a chemical process in action, the thing that we are investigating is called the system. Everything else is the surrounding, and together it's called the universe. When the system releases heat, then it's an exothermic reaction because it releases heat in terms of delta H negative, but the surrounding is absorbing that heat. So delta H will be positive with respect to the surroundings. Okay, and we're going to do a lot of that in thermodynamics. So I'm going to skip that and I'm going to go to enthalpy. When we talk about enthalpy, we're talking about the heat that is generated. Okay, the heat that is generated when a reaction occurs. So here we are. Okay, and you've seen it in kinetics in terms of you have an initial energy of the reactant, you have a final energy of the product, and that energy difference is the heat that is either absorbed or released. When we talk about energy of a reaction, we have to look at the heat and the work that it's capable of. And you guys sort of covered this in thermo chemistry, in general chemistry, okay? So the internal energy, if you have a fuel, gasoline, for example, then there's a bunch of internal energy due to the bonds. And that internal energy can do useful work for you, W, like running your car. But in the process of converting that chemical energy to mechanical energy, you also lose some heat because it's always going to be a waste product in that conversion. And so that's the equation that you see here, that the internal energy is going to be equal to the heat plus the work that is associated with that. Now, there's a first law of thermodynamics, and the first law of thermodynamics simply states that energy cannot be created or destroyed. It's only converted from one form to the other. So in other words, the energy of the universe is constant. That's excluding, of course, Einstein's famous equation, E equals mc squared. So we're not even looking at that. We're just saying that the total energy, if we have it, you can't destroy it. You can't recreate it from nothing. You can only convert it from one form to the other. And that's this equation right here. This right here is nothing more than the first law of thermodynamics. That therefore, if the energy is conserved, okay, and energy, internal energy equals the heat plus the work, then we can also say that the heat of the system is equal to negative the heat of the surrounding because it's conserved. Whatever the system releases in terms of heat, the surroundings has to absorb. Those are the only two components in our universe. Whatever work that system generates, the work has to be absorbed by the surroundings. If the work is absorbed by the system, it's got to come from the surroundings. So we have a simple universe. The universe consists of the system and the surroundings, and those are the only two that communicates. Okay, so that's what all that discussion was about. Now, when we have a reaction, reactant converts to product, then generally, when bonds are broken and bonds are formed, you've got a heat, an energy that's involved with that. And so we call that delta H of the reaction. Like, for example, the combustion of methane to carbon dioxide and water, that produces energy. We call that energy delta H combustion because it's a combustion reaction. Carbon plus oxygen forms carbon monoxide. We call this delta H formation. And you might ask yourself, why is it called formation? Wasn't a formation based on what we talked about in equilibrium, the formations from transition metals reacting with some other substance? Yeah, I know, we like to confuse beginning chemistry students. The reason why we call this formation is because we are forming a chemical, CO, from its elemental source. Okay, the formation that we talked about in equilibrium, forget about that. That's a different formation. The formation here is because we're forming a chemical from its elemental source, its elemental abundant source. So if you got nitrogen and oxygen, and that's the natural abundant source, and you're forming nitrogen dioxide, that's a formation. Okay, that's a formation. Oxygen and hydrogen forming water, that's a formation reaction because you're forming a chemical from its elemental abundant source. Solid going to a liquid, that's melting, right? We call that fusion in science, fusion. So this is delta H of fusion right here, the energy associated with that. What of course happens is that this is an endothermic process. You can't get ice to convert into a liquid unless you add energy. So delta H fusion would be positive in this case. Delta H combustion for methane would be negative because you're releasing energy. So we have signs. When we take a liquid and we convert it to a gas, that's vaporization. Again, that's positive because you can't take a liquid and convert it to a gas without an input in energy. So it's an endothermic process. Endothermic process is delta H that are positive. So this is called hydration, the energy associated when an ionic substance absorbs water from the atmosphere. That's basically it. So it's all energy associated with a reaction, but we like to be specific. That's why we give it specific names here. Okay, so the audience will understand the chemical process that's taking place. A lot of times what we do is we measure these energies, but we don't have an absolute scale. What do I mean by that? Okay, the way we define elevation, for example, in this planet is based on sea level, right? If we are so many feet above sea level, then that's our elevation. So the elevation of buildings, of land, of mountains is based on a relative scale. The sea level, of course, sea level keeps going up and down, but that's what we measure. Now, if we wanted, say, another scale, we can measure it from the bottom of the seafloor. But again, it's all relative to that point of view. We do the same thing in terms of energy. What we have an absolute scale on is temperature. We know where the 0 point is. The 0 point for temperature is absolute zero, 0 Kelvin minus 273.15 degrees Celsius. That's our 0 point. Nothing can go below that. And then everything else is positive from there. Okay, so that's an absolute scale, unlike elevation. When we measure something, then we generally have a scale. Okay, we take measurements. When we measure energy, do we have an absolute scale or do we have a relative scale? Take, for example, this car. This car sitting on the road, and we can say that, oh, it's not moving, the engine's not started, so it must have zero energy. And then somehow the brakes were released and starts rolling downhill. Well, if it's rolling downhill, then it's losing energy. Where did that energy come from? Well, you can say that, oh, because it was parked elevated, then it had a certain amount of potential energy, and now that potential energy is converted over to kinetic energy. Now it's at the bottom of the hill, and then we can say, okay, now it's got zero energy. But in reality, that car is made out of molecules. Those molecules have protons and electrons. Those electrons are moving. And then if you think about it, the whole world is moving. So it's very elusive to get a zero energy. What we need is a relative scale. And that's what we do in thermodynamics. We have a relative scale for energy, for enthalpy. And what is that relative scale? Well, it's going to be based on some standard states. If we have the standard state, we know what conditions we have, then we can assign that zero energy, and everything positive or negative from that will be either positive energy or negative energy. But negative energy doesn't mean that you have negative, you're destroying energy. It's just relative because just like we have negative elevation, okay? Death Valley is about 550 feet below sea level. Same thing with energy. We can have a negative energy relative to our scale. So you need to understand that. What is exactly our standard? Well, we measure things at 1 atmosphere. That's fine. That's the same that you guys learn in general chemistry. But instead of 0 degrees Celsius, we measure things at 25 degrees Celsius. That's the standard state. Whenever you have 1 atmosphere, 298 Kelvin or 25 degrees Celsius, we have standard state. We got to define standard state because that's going to be our 0 point for certain chemicals, okay? So the other thing that we need to remember is that the chemical has to be pure. Like water is not pure. It's got hydrogen and oxygen. What I mean by pure is like pure helium, pure oxygen, O2, pure carbon, graphite. Chemical has to be pure. It's got to be liquid or solid in its pure state. If it's a gas, it's got to exist at 1 atmosphere. If it's a solution, it's 1.0 molar. Okay, so that's how we define standard state. Standard state, the super zero, we put that in the designation of the letter or the symbol we designate. Like E represents energy, H represents enthalpy, S represents entropy, and G represents free energy. Okay, so right here, delta H0 formation. Well, at 25 degrees, we can assign graphite, because that's the way we find it in abundance in nature, 0 energy. Oxygen, that's the way we find it in nature, 0 energy. And then when we measure this reaction, we get a certain amount of heat that is released. That heat translates to 393 kilojoules per mole. And so we can say that we can assign carbon dioxide a formation enthalpy of 393.5 and oxygen and graphite 0. We can do the same thing for formation of nitrogen dioxide. Nitrogen is going to have 0, oxygen 0. And when we measure this reaction and we measure the heat that's required, we see that it needs 33.84 kilojoules per mole. So the formation constant for NO2 is plus 33.84. That's how we make our scale. That's how we make our scale for thermodynamics, which you guys will be using a lot of. Okay, so the standard heat of formation is something that we measure because we assign certain chemicals 0. And if we can assign certain chemicals a 0 and we can measure the heat that's either generated or absorbed, then that chemical that is being produced is going to own that energy. Okay. And so what are the chemicals that we assume 0? Everything in its natural state, okay, in its pure elemental state. So bromine at room temperature is a liquid, not a gas, not a solid, but a liquid. Oxygen at room temperature is a gas. So carbon in its most abundant state is graphite, not diamond. Diamond, it's one of the more rare state. Sodium at room temperature is a solid. So we assign the enthalpies for these chemicals 0. What is not 0 is water. Why? Because water is not a pure element. It's got hydrogen and oxygen. Oxygen liquid, yeah, it's a pure element, but at 25 degrees, it's not a liquid, it's a gas. Okay, carbon graphite is not the most abundant form for carbon. And sodium chloride, again, that has 2 elements that are involved. It's not a pure element. So these will actually have a delta H formation that is non-zero. I want you to think about that, because what will happen is that we're going to use this scale, these thermodynamic scales, to calculate delta H of a reaction based on certain tabulated value. And then we're going to use the same concepts to calculate entropy and free energy. Okay, so that's all I have in terms of this particular section.